Okay, so a nonlinear discrete time model can be represented by a set of first order difference equations in which each of the states is incremented based on a function that depends on the present values of the state. So x1 of k plus 1 is a function, I call it f1, of x1 of k, x2 of k, etc., xn of k. So I'm assuming that I have a system of order n. And I write n of these equations. And of course, I need to start with some initial conditions. So I specify the initial conditions for the state, and then when I want, for instance, to model the evolution of the state, I just iterate this equation. This, I think, is no doubt for anyone, but if you have any doubt, please interrupt me. And you can define the state vector x and a vector of functions f, and you write those equations in a compact way in this way. So this is a matrix notation or vector notation for the nonlinear state model with some initial conditions. Now, when you write x of k plus 1 is equals to f of x of k, you don't have the so-called control variables here. This is what I call an autonomous system. It depends only on itself. In general, in control systems, we must have a vector u, which is the vector that we can manipulate. That's the inputs of the system. Now, if you want to study stability, you can't have this u. So what happens? If you want to study the stability of coupling this controlled state model together with control law that generates u, observe that u is generated as a function of x. So you get rid of the u, and you will have here f of x of k and some function of x of k. Okay, so again, we are in the above form. The difference is that the f is no longer the open loop one. So this is the idea. And now we are going to concentrate on uncontrolled Lyapunov systems, that is to say, systems of this form, x of k plus 1 equals to f of xk, just that, because this is what appears when we have a controlled system and we study the stability of the coupling it with the control law. Now, we have discussed that in perhaps the first lecture, what is an equilibrium point? An equilibrium point is a value of the state, let's call it x bar, such that if you start at x bar, you will remain at x bar. So this means that if xk is x bar, then x of k plus 1 is f of x bar, but if x bar is an equilibrium, you will remain there. So xk of xk plus 1 will also be x hat at x bar. Okay, and to find the equilibrium of a nonlinear system, you have to solve this in general nonlinear equation, and you can have several solutions. Let's see one example. Suppose that you have the system defined by these two equations. So we have, this is a second order system. You have a nonlinearity here. Okay, so this is x2 squared. And alpha and beta are parameters. Let's assume that alpha and beta are parameters that are different from 1. Now, to obtain the equilibrium points, you just assume that all the x's are a constant version x bar. So you replace x1 of k plus 1 by x1 bar, x1 of k by x1 bar, and so on. Okay? So you end up with a system of nonlinear equations. You should notice that there is a x bar, x2 bar squared here. So what can we do? We can express x1 bar in terms of x2 using the second equation, replace it on the first equation, and then we get second order equation on x2 bar that we can solve. Okay, I'm not going to show all the computations. That's a good exercise for you to do. And you get this equation for x2 bar. It's a second order algebraic equation that you can solve. Of course, one of the solutions is x2 equal to x2 bar equal to 0. And if x2 bar is equal to 0, you look at the second equation. So this becomes 0 equals to x1 bar plus beta 0, which is x1 bar equal to 0. So one equilibrium point is 0, 0. And the other equilibrium point is 1 minus alpha, 1 minus beta. So if x2 bar is not 0, you can divide everything here by x2 bar. And x2 bar will be 1 minus alpha, 1 minus beta. So again, you replace it here on the second equation and you solve it with respect to x1, and you get this other point. So you have one equilibrium point, which is 0, 0, and another equilibrium point, which is given by these expressions. Okay. So the point here is an example in which we have a nonlinear system, and this nonlinear system has, in this case, two equilibrium points. It can be any number. It can even be an infinite number of equilibrium points. Now, we speak a lot about stability, and actually there are several notions of stability. We are going to use the so-called stability in the sense of Lyapunov. So I tried to make a sketch here where we have this dot, this black dot in the center. It's at x bar, our equilibrium point. And I want to define, this is a definition, so it's not a result, it's a definition. What do we mean by stability, instability, and so on? We consider, first of all, we consider this largest ball, okay? I represent balls by the symbol S for sphere, of center. Well, this should be x bar, the bar is there, so this is a typo. So center x bar and radius RO. Okay, so the distance between any point in this sphere to the center is RO. Okay, and this largest sphere is where you are going to concentrate your efforts. So your saying that the equilibrium is stable or unstable is valid with respect to this large region. Could be the whole space, okay? But we are concerned with local notions. If R0 could be infinity, then we would be speaking about global notions of stability. So this being said, let's concentrate on the other two bars. And the definition of stability is a kind of game, okay? And what is this game? Suppose that I play a game with one of you. Let me call Tiago, okay? So Tiago, I'm playing with you, and you say, I specified a value of R, of capital R. So Tiago specifies the radius of this ball, this dotted line ball, okay? And he gives this value to me. And I should be able, if the equilibrium is stable, I should be able to find a smaller ball of radius small r, this other ball here, okay, the smaller ball, such that if I start at any point inside this ball, apart from the equilibrium, of course, if I start at equilibrium, I stay there. But if I start at any point, I should be able to stay within the ball specified by Tiago, the one of capital R. Now this, Tiago can say, well, I select, you were able to do that, okay, but now let's have a capital R which is smaller. And I should be able to find another small r, which is probably smaller, and so on. So for any of the radius of this dotted line that Tiago specifies to me, I should be able to find another smaller ball such that if my initial condition starts in this smaller ball, whatever the initial conditions are, it will remain inside the dotted line. Okay, that corresponds to this orange line, orange trajectory. Of course, this will be discrete because we are having dots. So, but I just represented the sequence of states by a continuous trajectory. Okay, so the definition of stability is if for any capital R within some bounds should not be bigger than R0. If for any of this capital bar, I'm able to find a small r such that if the initial condition starts inside the smaller ball, it will remain then within the largest ball. And if this happens for any larger ball, then I say that the equilibrium point is stable at least. Now, any question? Okay. Now I can ask a little bit more. I ask, the state will not only remain within the dotted line, but it will remain, it will return to the equilibrium point, approach asymptotically to the equilibrium point. So this is asymptotic stability. So the point is said to be asymptotically stable if, in addition of being stable, all the trajectories return to the equilibrium. Okay? The equilibrium points that are stable but not asymptotically stable, sometimes they are also called marginally stable or just stable. Okay, so in both cases we have stability. And an unstable point is that is the one that no matter how I squeeze my small r, so I squeeze this smaller ball, there are initial conditions that lead me to go away out of the larger sphere. Okay? You should bear in mind that this must be not just for a particular initial condition, but for any initial conditions apart, of course, from the equilibrium point. We know that at equilibrium point, if you start there, you stay there. Okay? A point is unstable if it is not stable. Any question? Okay. Now, the key point that was a definition. And we want to have a method to see if a given equilibrium is stable or asymptotically stable. And the method relies on this notion of Lyapunov function. So what is the Lyapunov function? It's something that measures the distance with respect to the equilibrium point. Okay, let's see how. So I define, this is the definition, okay? The Lyapunov function is a function of the state. So if you look at the picture, our state, state space has dimension 2, so I have two variables, x1 and x2. And for each point in state space, at least in a region omega, so some ball around the equilibrium. Let's suppose that equilibrium was here, where I have my pointer, and then I have some omega region around it. Okay, and within this region, for any state, I have a correspondence with a real number that defines V. Okay, so for any x1, x2, I have a V of x1 and x2. And this V must be a continuous function of x1 and x2. It must vanish at equilibrium, that is to say, V of x bar is 0, but it must be strictly positive outside from the equilibrium point x0, x bar. So actually, this means that V must have a minimum at the equilibrium point. Now, apart from these two conditions, I have another condition, which is this. Suppose that I start at some initial condition. Look at the diagram. So I start in the plane x1, x2 at some initial condition x0. So I complete x1 and x2 and so on. So I have a sequence of points. And I take two consecutive points arbitrarily. Okay. For any of these points, there are states. So for these states, V is defined. So at x0, I have some V of x0. For xk, I have some V of xk, etc. Now, when I move along a trajectory, for V to be a Lyapunov function, the V must be non-increasing. That is to say, it must be either, it must decrease or at least become constant. Sorry for my throat. It's not yet completely well. And this must be for any trajectory, not just for one trajectory, but for all possible trajectories. Okay? So for all possible trajectories, when you move from xk to f of xk, the difference of the corresponding values of v must be smaller or equal to 0. That is to say, v is decreasing. Okay? Suppose that they are negative. If they are negative, you will have to approach the minimum. Okay, that's why I say that V is a kind of measure. The larger the V, the farther away you are from the origin. Okay, and if V is always decreasing, this means that your state is approaching the minimum. Okay, this is not a proof, but the proof of the method of the direct method of Lyapunov actually is quite goes along these lines. It's not much than what I just said. So suppose that we have this dynamic system, x of k plus 1 equals to f of xk. If you can find the Lyapunov function v of x in a certain region, around a certain region of the equilibrium, then the equilibrium point is stable, at least. It can be asymptotically stable if the increase or the variation, sorry, better to say, the variation of the Lyapunov function is strictly smaller than 0. Okay, so this is the result. In continuous time, this means that this is the total derivative of v with respect to time along the trajectories. Okay? Here, it's the difference. It's even simpler. Actually, sometimes this can be not so easy to handle in an analytic way. Let's see one example. Suppose that we have this second order system, which is nonlinear. So you see that this is f1 and this is f2, and these are nonlinear functions of x1 and x2. You can easily see that 0, 0 is an equilibrium point, because if you start with x1 equal to 0 and x2 equal to 0, what do you get? In the first equation, you get 0 divided by 1 plus 0, which is 0. So you start with 0, and the next point is 0 for x1. And on the second one, if you start at x1 equal to 0, x2 equal to 0, you get again 0 divided by 1 plus 0, which is 0 divided by 1, that's 0. Okay, so next x2 will be 0. So 0, 0 is an equilibrium point. And now I try what I call a candidate Lyapunov function. So I have the hope that this can be a Lyapunov function. If it is a Lyapunov function, I'm a rich man, because then I can conclude stability. Now, the first thing, 0, 0 must be you must vanish at the equilibrium point, which is 0, 0. So for x1 equal to 0 and x2 equal to 0, 0 squared plus 0 squared is 0, so v of the equilibrium is 0. And it's continuous because this is a sum of polynomials, so you don't have any discontinuity. There are no values of x1 and x2 for which v is discontinuous. So let's now compute, let's now test the difference, okay? So we must check this property that v of f of x k minus v of x of k is smaller or equal to 0 to conclude stability. Okay, so compute v of x of k plus 1. Again, I found here a typo. There is a curl here missing. Falta aqui parênteses. Use the definition. The definition v of x of k is just x1k squared plus x2k. Now, v of x of k plus 1 is x1 k plus 1 squared plus x2 k plus 1 squared. Now, use the equations that define the trajectories. Okay, so use these two equations to express x1 of k plus 1 and x2 of k plus 1 in x1 of k and x2 of k. So I use these equations here, nothing more. But now I have a sum where the denominator is the same, so I can write this sum as x1k squared plus x2k squared divided by this denominator. But the numerator is nothing more than v of x of k. Okay? In the denominator, is, well, it never vanishes because I have x2 squared, x2 of k squared, so this never vanishes. There is no danger that I get here something which is -1. And this is a number which is bigger than 1 because it's the square of something which is bigger than 1. So this is smaller or equal than v of x. Okay, so I can conclude that v of x of k plus 1 is smaller or equal of v of x of k, so the equilibrium 0, 0 is stable. At this point, I would like to ask you if you want to ask something, or you want to make some comment, or okay. So we have this tool, and now let's apply the tool to our main business, and our main business is to prove stability of a predictive control algorithm. So Suppose that we have a nonlinear plant model. X of k plus 1 is equal to f of xk and uk. And let's assume that this plant is such that the origin is an equilibrium point. So if you make x equal to 0, u equal to 0, you get a state which is again 0. And you compute u according to a MPC, so to a receding horizon strategy. That is to say, you are at time k, you consider a cost, a receding horizon cost, so cost over an horizon, which is written here, okay? And this cost is the summation of some function I represent by L. And what are the properties for this L? This means that this function can be probably something, not just the sum of squares, but other things. It must be bigger or equal to 0, this L. It will be 0 if and only if, this is not a typo, this EIFF means if and only if. So the L function, L of x and u, vanishes if and only if x equal to 0 and u equal to 0. And furthermore, it satisfies the so-called regression property. That is to say, if you consider this vector that results from concatenating x1 and u1, and if you take the norm, then when you decrease the norm, you will decrease the value of L. Remember that L is positive. Okay, so this is a very large class of problems. We have possibly nonlinear dynamics, and we are considering many possibilities for the cost. They must satisfy these properties. Now, I'm going to find u by minimizing this cost in a receding horizon sense, which is something that you already know. But I'm going to impose a terminal constraint. That's the big trick. Okay, so I'm imposing that the state, the last state, the state of the fork. So when I do the optimization, I will assume that the last state will be 0. Okay, so I do the optimization under this constraint. How can I do it? Well, you can use the method of Lagrange multipliers, or you can use numerical methods later. We will discuss it. I can also have so-called operational constraints in addition to this one. This one comes out from, it's a so-called stability constraint, because I will use it to prove stability. But then I can say, well, my valve cannot be closed more than 10% and may not open more than, say, 70%. That's a constraint on you. Or my temperature that enters the state cannot be higher than 250 degrees. That's, again, a constraint on X. Okay, so I'm assuming I'm solving my problems under the assumption that future use and future X, or predicted use and predicted X, better to say, will be within some sets, script capital U and script capital X. And these are prescribed, and we know that from the formulation of the problem. Okay, if you solve this problem, okay, and you apply this control law, the equilibrium x0, u0 is stable, provided that the optimization problem is feasible. That is to say, that I can find the sequence of u's and the corresponding sequence of x that minimizes this, because we have a lot of constraints, and we could not find a solution. So feasibility means that we can find a solution for the optimization problem, And then we solve this optimization problem at each step according to the receiving horizon strategy. Okay, so actually the result is quite simple. For a wide class of problems, we can take advantage of this terminal constraint and prove stability, which I'm going to do in a moment. One should, before doing that, one should be careful because feasibility, we don't have an easy way to find out whether the problem is feasible or not. Okay, so there are no theorems in general, apart from trivial problems. There are no theorems that ensure feasibility of a problem. So we are assuming that the optimization problem is feasible. If it is feasible, then we can prove stability. Okay. Now, this is one of my famous slides in which I tried so much to explain things that they become very complicated. I hope not. I hope not. So, what we want to do? We want, okay, let's look at this. We have our costs, and I want to compute, if I want to prove stability, I want to compute V of k plus 1, subtract it from Vk, and show that this is smaller or equal to 0. Or in another way, I want to prove that V of k plus 1 is bigger or equal than V of k. Okay? In that case, I can take the cost as a Lyapunov function, which is quite natural. So let's write V at time. Okay, now I'm changing a little bit the notation, but this T is the time. Okay, this T is the time. So I want to compute VO along the trajectory. This is the optimal cost. That's why I put VO. And I want to then manipulate the expression of VO to compare it with VO of T. Okay? So let's start by just observing that V of T plus 1 is what we had before here, but now with T or K replaced by T plus 1, by T plus 1. Sorry. Okay, so I place here T plus 1. Here I had T minus 1 plus I, so this becomes T plus I. Okay, so this is nothing more than writing the cost at time T plus 1, and then I minimize with respect to the sequence of U starting at T plus 1. That's why I put a VO there. And then I will represent this mean of U. This U is a sequence of future U's. Now, I can write this summation. I can decompose it in several parcels. Look at the diagram. So please try to look at what we have here in the second line and the diagrams. So VO of T plus 1, look, I goes from 1 to H, so X goes from 2 plus I, from 2, for I equal to 2, for I equal to 1. This goes from T plus 2 up to T plus H plus 1, okay? That's this line here. That's this line here. And U goes from T plus 1 up to T plus H. U goes from T plus 1 up to T plus H, okay? So these signals form together VO of T plus 1. That's the black part. Now, if you write VO of t, okay, VO of t, you have to take one here and one here. So they go from t up to t plus h minus 1 in terms of u, and x goes one step more, x of t plus 1, x of t plus h. Okay? Now, they both together form VO of t. I want to relate VO of t plus 1, that is to say this black part, with this red part. Okay? So, the black part is the red part, but then you have this first point here, ut xt plus 1. So I have to eliminate or subtract this term because it does not appear in VO of t plus 1. So I put here a minus L of xt plus 1 ut. That's this first point. And then I have to add this point that does not appear on the VO part, the red one. Okay? And apart from that, I have will be VO of t. Okay? So, any question about this? So what I was doing was I wanted to relate this with VO of t. So that's a red line. So I subtracted this from VO because it does not appear on the black part, and I've added the last point. Okay, because this was not also appearing, one with the minus sign, the other with the plus sign. Okay. So I could prove this formula, and I can break this. I do the minimization. So I can think that I do the minimization up to not to the last point, but to the point before the last. Okay, so I go along an optimal trajectory along the first part. That gives me VO and this term here with the optimal control. And then I optimize again with respect to the last equilibrium, to the last control, the last point. This is just the last point. Okay? And this is actually suboptimal because this is actually it's not as good as optimizing with respect to the last point. So I put here, instead of an equality, I put an inequality because this term would be bigger, perhaps bigger, I'm not sure, but it will not certainly be less, but it will be probably bigger than this term. Then the optimal that would result from optimizing everything. Okay, so what do we have? What do we have? We have, sorry, oops. We have VO minus this VO of t plus 1 is smaller or equal than VO minus this term plus that term. So I repeat it here. Okay, this is just a repetition of the last slide. But now I'm assuming that I'm doing the optimization, assuming that the last state will be 0. And if you look at the plant dynamics, and you compare the state at time t plus h with the state at time t plus h plus 1, what you get? The state at time t plus h plus 1 is f of x of t plus h, u of t plus h. But this is 0. Okay? So the state at time t plus h plus 1 will be f of 0, u of t plus h. All the choices other than selecting u will lead to general states here, at time t plus h plus 1. Okay? So the best thing for you, and using the digression property of L, is that you select u equal to 0, t plus h equal to 0. Okay, this will lead to t of t plus h plus 1 equal to 0. So this is the minimum value of that term. Okay, any other choice will be or equal to this one if we by chance you get another x, which is the sequence, the next x will which would be 0, or but L would be bigger. Okay, so this is the best one, and since this is the best one, you can say that this will be 0. This minimum value will be 0, because remember, we were assuming that L of xu is 0 if and only if x is 0 and u is 0. Okay? Any other value of u would lead to an L which would be bigger. So by doing also this minimization, this term here assumes the value of 0. So your VO of t plus 1 smaller or equal than VO of t minus L plus, and this no longer appears. Okay, but L is positive. Okay, L is positive or 0. So you can take it away and conclude that VO of t plus 1 is smaller or equal than VO of t. And in this way, you have the assurance that VO is a Lyapunov function and you have stability. Any question? Okay. It's natural that this is not so easy. What was the important thing? We used as Lyapunov function the optimal cost, and we could prove that the increments of the cost of the optimal cost are smaller or equal to 0. So this optimal cost is really a Lyapunov function, and so we can conclude stability. That's the big issue. And it was fundamental to assume, to make this last term 0, it was fundamental to assume that we have the final state equal to 0. Now, let's discuss this a little bit more. What are we doing? We are we are by making this constraint, you are forcing the state to squeeze. You are squeezing, estão a apertar o estado. Okay, that's the issue that allows you to ensure stability. If you don't squeeze the state, it can be that in the last part, your U can be such that, remember the story of the restaurant, that U grows and X grows. But since this is in a very small interval of time, the last, along the optimization interval, so there will be a last period in which you relax control, you relax the state, because this will have not much influence, but it will, in the long term, give you stability. When you have a finite horizon, you are doing the optimization of a finite horizon, you don't notice. But if you let it go, then it would become unstable. And remember that you are optimizing over a finite horizon, then you are repeating the optimization. So you want this to be stable. And if you squeeze your terminal state, that means that you will do not allow this escape factor. Remember of the restaurant example, in which well, I'm going to sell the restaurant or to give away the restaurant, better to say. So in the last months, I don't care, okay? And as a consequence, probably the amount of money or the number of customers that come, it's very much reduced. And so the system is become actually unstable if you run it again in the same way. Now, you can think, well, but yeah, I don't do this. I don't do this because either I have respect to the guy that will come after me running the restaurant, or because I will receive some extra money by the final value of the restaurant. And this corresponds to keep the quality level squeezed around the correct value, okay, which would not be zero, but would be some value in the restaurant. Now, what happens here in practice? Suppose that we have a linear. Suppose that our dynamics. Let's go back. Sorry. Suppose that our f is a linear function. So I have linear dynamics, and our L is a quadratic function of x and y. Okay? And then that you don't have this operational constraint. So script u and script x are just the whole set of real numbers. In that case, you can solve this problem. In that case, you can solve this problem exactly. I will say something more about it in a moment. But if you start, even in the linear case, the linear quadratic case, so linear dynamics, quadratic cost, if you start imposing constraints, then it's not possible to solve. To have a closed form solution. And this means that you have to resort to numerical methods. And an equality constraint like this, forcing the terminal state to be zero, is very, very hard to solve in with an estimation, with a minimization solver. So people started looking for different approaches, and one of the approaches consists, actually there are more approaches than this one of the terminal constraints, but one of the approaches consists in imposing that the norm of the terminal state is not exactly zero, but it is sufficiently small. That is to say, the norm is smaller or equal than some epsilon, and you can prove a theorem. I'm not going to do it here because it's a little bit more complicated. But if the result is, if epsilon is small enough, then you can prove stability. Okay, and you can also extend these results for the situation in which you don't have a perfect model of the plant. So this constraint, this form of the stability constraints, is much more easy to deal with by numerical solvers also. Okay? Just to give you an idea, the equality constraints, the idea of the equality constraints appeared, say, around 88, 89, okay? And this appeared, say, 4 or 5 years later, just in the beginning of the 90s. And there were some groups tackling with this, Italian and British groups, and also there was another another approach based on modified or fake Wicat equations. There's a group of researchers from Belgium that did that approach, just to give you an idea, that appeared more or less in the beginning of the 90s. Okay. I would make a break, a 10 minutes break now. But before the break, would you like to ask me something? Okay, so it's 3 minutes past 3. Let's resume in 10 minutes at a quarter past in 11 minutes, a quarter past 3. Okay. So the first thing is controllability. And controllability is, the definition is this one. Suppose that I have a state realization or a state model of a linear system. X of k plus 1 is equal to A of x of k plus bu of k. And I say that this state is completely controllable, or simply controllable in the sense that all the states can be moved, or reachable. I will discuss this term reachable in a moment. In Portuguese, atingível, if and only if, for an initial condition at the origin, I can find a sequence of control inputs, U0, U1, U of capital N minus 1. Well, this capital N is a convenient number, such that wherever I specify this xf, x of n will be equal to x of n. So this means that the model is controllable if, starting from the origin, you can reach any point in the state space by selecting a sequence of control inputs. Now, how can I find in practice whether pair AB is controllable? I have a criterion that I'm going to show. And the criterion is this. I build this matrix. So I pick up vector B of the model. Then I compute AB, which is again a vector. And I put it as a second column of this matrix. Then A squared B, etc., up to A n minus 1, where this n is the dimension of X. And multiplied by B. So this, suppose that the system has just one input. This will be a square matrix, but this is valid for multivariable systems as well. If this is a square matrix, then I call it, in any case, the controllability matrix. And for the system to be controllable, the rank of the matrix must be n, equal to the dimension of X. Okay? Where does this come from? Where does this comes from? Let's prove it. And to prove it, I need the Cayley-Hamilton theorem. What is the Cayley-Hamilton theorem? Suppose that you have a square matrix, capital A, and you will remember from linear algebra that the characteristic polynomial is the determinant of Si minus A, where S is a complex variable. Okay, so this gives you a polynomial. where the A1, A2, etc., AN are real numbers. And the Cayley-Hamilton theorem says that the matrix verifies this equation here. Okay, so you replace S by A, and you get this stuff. Okay, so it looks like a trivial thing, but it's not, because you cannot just go to the characteristic polynomial and replace S, which is a scalar, by A, which is a matrix, and say that this should be equal to 0. So it requires a proof. We are not going to do the proof here. What is really interesting here? It means that you can express the power n of the matrix A as a linear combination of the first powers up to n minus 1. So remember that the identity is A up to 0. Okay, so you form a linear combination of the powers of A up to order n minus 1. The coefficients of this linear combination are nothing more than the coefficients of the characteristic polynomial, and you get an. Okay, and of course, probably it will be not much difficult to find A up to n minus 1, because you can express A up to n minus 1 is A1 times AN, and AN is a linear combination of the powers up to n minus 1. So you go on recursively, and you can find any power from n on as a linear combination of the first powers, of the first n powers of the matrix, from power 0 to power n minus 1. Okay, this is what we are going to explore. So this lemma actually is a different way of expressing what I just call your attention to. Suppose that you form a vector of in this way. So you pick up B, then a B, then a square B, etc., up to A, up to some capital N. Okay, this can be anything. B. Suppose that N is 1000. Okay, now, and you have a system of order 2. So if you have a system of order 2, you would have just B and AB. And the rank, that is to say, the number of independent columns in this large matrix is the same as the rank of BAB. Okay, see, if B and AB are, when I say B and AB, I refer to the second order example. If they are linearly independent, okay, the rank will be just 2. In any case, it will not exceed n. So in general, for a matrix or for a state model of order n, okay, the rank, the maximum number of independent vectors of independent directions defined by this large matrix is equal to the rank of just considering the first small n vectors here. How can we prove this? The proof is, okay, we start with the Cayley-Hamilton theorem. Okay, then we multiply on the right by B. This means that A and B can be expressed as a linear combination of the powers between 0 and n minus 1. Okay, so and then you go on recursively. You can use the recursive technique of proof, the so-called mathematical induction. Okay, so but apart, if you don't know, if you don't remember mathematical induction, which consists of, suppose that you can express A k, b for any k in terms of the powers, then it will, of the powers up to order n-1, then it will be possible to express also a of k plus 1b. That's then the idea is in an intuitive, is very intuitive, because you just go on and use this possibility of expressing all the powers, one power in the first ones. Okay, now suppose that you start from the origin and you iterate your model. Okay, so your xn will be, we have deduced this formula already, okay, where n can be as large as you want, provided it must be larger or equal than the order of the system. So what does it mean? It means that x of n will be a linear combination of these powers of n times b, and the coefficients of the linear combination are the values of the control between 0 and capital N minus 1. Okay, so if I specify xn, x capital N, then what I have to do is to find the coefficients u0, u1, u at n minus 1. Okay, and the states that I can reach are the linear combinations of these vectors here. But the independent vectors that I find in this large collection of vectors for capital N, they are also contained in the first n vectors, where n, small n, is the order of the plant. Okay, so I can reach any state provided in n steps, provided that these vectors are linearly independent. Okay, so if I go on in that more time instance, I would not be adding anything. So the vectors that are important are the first 10 ones between a0 and then a of n minus 1. A0 is the identity, so you don't see it here. Okay, so what is the conclusion? The conclusion is you can reach any point. You can solve the equation xf equal to this linear combination and solve the equation with respect to the sequence of u's, provided that with just the first n, where n is the small n equal to the state, with the dimension of the state. Okay, and this also gives you linear control auto reach. So if these vectors, in other words, if these vectors are linearly independent, the characteristic of the controllability matrix will be n, because the definition of the characteristic of the controllability matrix is the number of independent vectors that you find here. And you will be able to solve this equation here with capital N equal to n, and whatever the value of x that you place here. So you will be able to start from 0 and reach any point. Was my explanation a little bit spaghetti one? Want to make questions? Okay, so retain this. We have the concept of controllability. A pair AB is controllable if, starting from the origin, I can reach an arbitrary point. Okay, that's the definition. And remember that you should start from the origin and reach any point. So I call also this controllable or reachable. because I can reach something starting from the origin. Now, I want to see, let's say in practice, I want to have a criterion. So I compute this controllability matrix, I compute the rank, in Portuguese, the característica, that's the number of independent columns. And if the rank is equal to the dimension of X, then I can reach all the states that I want in n steps. I can say that more. Okay. Now, let's see one example. Let's see one example. Suppose that you have this system. Is this controllable? So you have your matrix A and your matrix B. How can you see whether starting from the origin you are not able to reach any point, any specified state that I specified? So I specified some point at any place, and I may not be able to reach that. So what is the more direct way of answering this question? Can someone tell me? No one? Well, if I'm able, if starting from any point at the origin, I can be able to, from the origin, I can be able to reach any point, the characteristic, the controllability matrix must have a rank of 2 because that's the size of the state. Just a moment. Okay, so I compute B and AB with this B10 and this AB1100. And I see the characteristic that's just 1. So the rank, which is just 1, so the rank of the controllability matrix is 1, smaller than the dimension of the state, 2. So this is not controllable. That is to say, from the origin, there are points that you cannot reach. Now, sorry. Consider now a different problem. Suppose that you are at some initial condition, a point alpha beta. Okay, so alpha beta is any point. And you ask, is there a control that leads me to the origin? So what are the equations that I must solve? Let's try to do it in one step. So the equations would be 0, 0, next step, equal to the matrix A times alpha beta, the point where you start from, plus 1, 0, UK. Okay. Does this have some solution? Yes. Yes. What are the solution for U0? Is just alpha plus beta plus U0 is equal to 0. So U0 should be minus alpha minus beta. Okay. So from any point, from any point, you are able to reach the origin. From the origin, you may not reach any point, all the points. There are points that you cannot reach. But from any point, whatever you choose, you will always be able to reach the origin. Okay, so I call this concept of being able to move a state to the origin, controllable or controllability to the origin. Okay, so moving away from the origin, I call it either controllable or reachable. Moving from any point to the origin, I call it controllable to the origin. Okay. In continuous time, the two notions are equivalent. In discrete time, they are not, as you can see by this example. This system is controllable to the origin, but not controllable in the sense that it's not reachable. So if you apply that criteria of the rank of the controllability matrix, it will fail. Okay, so bear this in mind, and that this is a major difference of discrete time systems and discrete time systems and continuous systems, because in continuous systems both notions are equivalent, but in discrete time they are not. Okay, any question? Okay, this is the comment on reachability. Then another important notion is the notion of stabilizability. That is to say, a system is stabilizable if there is a state feedback U equals to minus F of X, okay, such that it becomes stable. That is to say, when I replace U by minus F, the equations become X of K plus 1 equals to A minus BF X of K. And the eigenvalues, that is to say, the poles of A minus BF, must be inside unit circle. Okay? So if I can find an F such that A minus BF has all the eigenvalues inside unit circle, the system is stabilizable. Sometimes, well, there is a connection, an important connection between placing the poles where you want and controllability, which we are not going to discuss here. But if a pair AB is controllable, then you can move your closed loop eigenvalues where you want. You can place your closed loop poles where you want. Okay? Now, here, this notion of stabilizability comprises a little bit more of systems for which there are modes that of oscillation. Modes of oscillations associate them with poles that are not stable, that are not controllable. I cannot move them by feedback, but they are naturally stable. Okay, so I cannot affect them, but they are stable already. And this gives the set of stabilizable systems. Another notion, important notion for the theorems on stability and so on, is observability. Now, in observability, I don't care about control because control will just shift things. I have a model which is X of K plus 1 equals to A of X of K, and then I do observations. Okay, and this C, typically in many cases, simple cases, Y is a scalar, so C is just a row vector. And I say that the pair AC is completely observable or simply observable if there is a time k1, a finite time k1, such that if you observe y between 0 and k1, you can infer the initial state. Okay, so you are looking at y, and if you are able to find out the initial state, then you will say that the system is completely observable. And the criterion is that this matrix, called the observability matrix, has a rank which is the dimension of the state. Now this time matrix depends on C and A. Okay, the previous one were A and B. Finally, we have the reconstructability. So observability means that you are looking at your output and you are able to infer what was the initial condition. In reconstructability, you are looking at the output and you are able to find what is the last state. Okay, so if there is a window of time, you are at time k. Okay, and if there is a window of length k1 or k1 minus 1, such that you observe it in k and k minus k1 and k, and you observe the y's, and you are able to find out what is the last state, then you say that this is this system is reconstructible. This state realization is reconstructible. An example is given by a state which is made of the last samples of the output and the last samples of the manipulated input. Okay, this is a non-minimum state. It is controllable, not observable, because it is non-minimum, but it is reconstructible. Can you explain me why this is reconstructible? N and this N is the order of the system, typically. Who can tell me why this is reconstructible? It's very simple. How many samples do you need to find out the last state? No one dares to speak? O gato comeu-vos a língua? Look, the state is made by the observations of y and u. So if you wait for n samples, you will get the state. It's just then the last 10 observations, okay, of y and u. Okay. This is very useful because state estimation becomes trivial. You just wait, and you have your state without the need for any special algorithm. Okay, now let's use some of these concepts here. Suppose that I have MPC problem in which my cost is quadratic. I'm assuming that U is scalar to simplify things. And so the penalty on the state is a quadratic function of the state. And so I want to minimize with the sequence of predicted values of U, subject this given by this quadratic function, subject to the dynamics, and imposing the terminal condition on the state. And I have no operational constraints, so I don't have any other constraints saying that U must be some minimum and maximum values of the state or something like that. I'm assuming that AB is controllable. A and this matrix that I call square root of Q is observable. Well, the square root of Q is any matrix or any vector such that the square root transpose times itself gives Q. Q is symmetric, so usually in all cases for a symmetric matrix, you can write Q in this form. And rho is positive definite. Rho is the weight on U square. Okay, so if you have this controllability and observability, if you verify this controllability and observability conditions, then you can prove stability of the MPC. Okay, this depends on this fact. And the solution is given by a feedback of the state where this F has to be computed from the model and the weights of the cost. The way to compute F can be done with the method of Lagrange multipliers that we have mentioned before. It's an application of the method of Lagrange multipliers. And I will include this in the exercise, solved exercises. Okay, now a final comment about this controller, linear quadratic MPC with stability constraint. In practice, this is more the formulas to compute F are more complicated than with the linear quadratic problem by solving the LQ problem, and you don't earn nothing because the LQ also give you stability. So the powerful, remember that the powerful of MPC appears when you have operational constraints. You have operations you have constraints, for instance, on U, in which case the control is no longer a state feedback, like here. But it is interesting to see what the result for which we have a stability, the algorithm for which we have a stability result gives when we have this limit simple case. So, any question? Okay, someone sent me a chat message asking for the exercises. By the end of this week, I will start posting a list of exercises for you to study. Okay, probably not all at the same time, but I will do an effort so that you will receive them by the end of this week. Okay. I see it's now 12 minutes to 4 o'clock. I will stop here. It took me a little bit longer than I expected, but we have time. And I will start the chapter on state estimation on Wednesday. I will also present a lecture via Zoom. Any final question?
Yeah, good afternoon, Professor. I have some colleagues of mine that asked if you could upload the recording of this class to Phoenix.
I will do it. I will do it. Also, the previous
Thank you very
one.
much.
I will do it. It takes the process is not simple because there is a conversion. There is a conversion done by Zoom, and then there is another conversion done by YouTube. That's where I posted. But I will do now both of them. The conversion done by Zoom is automatic in the end. Actually, I can stop.
Okay, no worries. Thank you.
But I will do it. It will take some time, but today you will have it.